All right, so today we are starting sort of the very last thing that we're going to do this year, which is about graphing functions that are sine functions and cosine functions. We aren't going to do tangent functions just because they're kind of another whole deal, but we're going to do sine functions and cosine functions, and then we're going to talk about why they matter, what we do with them, and then we'll do a little equation solving later maybe next week too. So we're working with learning target 13D, which is about that. And so I should just cross off this because we're not going to get to that this year. So I'm just going to cross that off. Yeah. Okay. So announcements for you. Hopefully you are watching this video the day that I assign it, but if you're not, it might be too late. Your last day of school is the 11th of June. Seniors, if you have an F in my class, you need to get your stuff done by midnight on Wednesday of next week, which is the 9th. If you're a junior, you have 2 more days because seniors have to know whether they're going to graduate or not. So juniors, you have a couple more days. You need to get that stuff done by midnight on the day that I tell you. Juniors and seniors have different days. I can't give any extensions this quarter just because it's the end of the year and there's just no flexibility on that. We just have to end the year at the end of the year. So today's lesson is about the graphs of sine and cosine functions. We can say that the inputs are the angles, and the outputs are the values of the trig functions. So I'm going to write the value of the trig function like that. And so we can figure out, okay, well, how do these things relate? And because we know some stuff about the unit circle, this stuff should be relatively painless, hopefully. Okay, so I'm going to start by kind of doing this by hand. And I'm going to be thinking about sort of the unit circle for a second here, but then I'm just going to kind of rattle these off. So if we remember back to our unit circle, here's our unit circle sketch. And we remember that the angles are kind of like that, right? What I'm going to do is I'm going to look at, well, what is the sine value of each angle? So what I'm looking for is I'm looking for this y value. This is a little bit confusing. The input values in our sine function are angles. And we're going to stay in radians. And then the output values are the values of the sine function. So I'm using the exact values to get my answers, and then I'm going to put these in my calculator to get decimal answers too. So what is the sine of 0? Well, it's 0. What's the sine of pi over 6? Well, it's 1/2. This one is root 2 over 2. I'm going to zoom in a little bit more so it's a little easier for me. This one is root 3 over 2. And then this one is 1. So if you remember, I'm kind of going around the circle and finding those y values around that circle. Okay, so then the sine of 2 pi over 3 is square root 3 over 2. 3 pi over 4 is square root 2 over 2, 1/2, and then 0. Okay, 7 pi over 6, negative 1/2. Oh, I'm doing this in the wrong box. Negative 1/2, negative root 2 over 2, negative square root 3 over 2, and then negative 1. Negative square root 3 over 2, negative square root 2 over 2, and then negative 1/2, and then 0. So what I notice here is there's sort of a pattern here. It kind of goes, these values go up, and then they come back down, and then they go back up, but kind of negative, and then they go back down, but they're still negative. So there's sort of a pattern here. There's something that's kind of like cyclical or periodic going on here. So now what I want to do is I want to get the decimal approximations. I'm just going to do this without you having to watch that whole thing in the calculator. And then I'll put those on there, and then we're going to continue from there. Okay, so here are the decimals. And so now what I'm going to do is I'm going to kind of draw my graph. And so I'm going to start here. I'm going to say, well, this is 2 pi. Let's call this 2 pi. And so then if I approximate, this would be where pi is. This is where pi over 2 would be. This would be where 3 pi over 2 would be. And then if I split those in half, this would be where pi over 4 is. 3 pi over 4, 5 pi over 4. And so what I'm doing is I'm putting those angles on the x-axis. I made a mistake. I'm putting the angles on the x-axis to show, okay, well, these are the input values of the function. And so then the next ones I would have would be, this would be my pi over 6. This would be my pi over 3. This would be my 2 pi over 3. This is a little bit tricky for me to think about. This would be my 5 pi over 6. And then this would be like 7 pi over 6. This would be like 5 pi over 3, 4 pi over 3. This would be 5 pi over 3. And then this would be, it would be 11 pi over 6. So these are a little bit tricky, but there we go. So now I have my x-axis labeled. And now what I'm going to do is I'm going to draw my y-axis as these numbers, the ones that are highlighted in gray here. So these numbers need to get graphed now. So over here, I'm going to make my y-axis go by 1. So I'm going to make this 1 way up here, and this is -1. So this would be 0.5, and this would be -0.5. And now we're just going to kind of do our best to approximate what this graph looks like. So here goes. Okay, here we go. 0, pi over 6 is 0.5, 0.7, 0.8, and then 1, and then 0.8, 0.7, 0.5, and then 0. And then kind of looks a lot like the same there. This is not perfect, but it doesn't have to be. It's okay. Nobody's perfect. Just kidding. Okay. Nope, just made a mistake. That one's big. So it kind of looks like this function. And that's actually a pretty nice graph, I will just say. This is the graph of y equals sine of x. So the inputs are the angles, the outputs are the values of the sine function. I was going to do this whole same thing with the cosine function, but I kind of think you get it. And so I'm going to kind of sketch this. I'm going to put the answers on here and then quickly sketch it, and then I'm going to move on. Okay, so these are kind of my answers, and then I'm just going to kind of quickly sketch this. And so I'm just going to give you a general picture. Here's where 2 pi is. This is where pi would be. And so what I see, I'm going to fix that. I'll put pi right here. That would mean pi over 2 would be here, and 3 pi over 2 is here. And so what my graph looks like really is, what you need to know is that this is 1 and this is -1. So the graph is going to look like this. Oh no. Kind of like that. There it is. So this is cosine of x, y equals cosine x. Again, the inputs are angles, and the outputs are values of the cosine function. What I do want to say here is that the cosine and sine functions are very, very similar. They just almost look like they're off by a little, like they start in different places, but they basically have the same curve, the same shape, the same characteristics, just a little bit off. I know that I have a lot of words here and I think it's factual information, but it's just kind of like too much stuff for me to say. But what you need to know is that the inputs are the angles, and the outputs are the sine or cosine values. Okay, so the input is the theta, the output is the trig ratio. Okay, so what we just saw on the last thing that I kind of talked about on that separate video is that those two functions, both sine and cosine, repeat over and over and over again. And the reason, and that's not a reason, the word that we use to describe that fact that they repeat over and over again is called periodic. So the word periodic, all it just means is that it repeats. So I'm going to write repeats here. It repeats exactly the same as it did the last time. So that's an important part. You know how periodicals are like magazines that come every once in a while? And so that's where it's sort of the same word. Okay, so the red graph is y equals sine of x. So that starts here and it goes up and comes back down and then it goes back up. The cosine graph is the blue one. And so it starts up here and goes down here and comes back up. Okay, so notice that the blue and red graph really are very, very similar. They have a lot of the same characteristics. It's just that it's sort of about the starting value. The word period is about how long the space between where the function starts and where it starts repeating again from that same spot, how long that space is. So the space between the starting value 0 and the next time it hits 0, like in the same place on the graph, see, here's the thing. This curve is like an exact copy of this one, and it's an exact copy of whatever's happening over here. And so this part right here, this is one period. So I would write 1 period. So one of the challenges of graphing these functions is figuring out what is the period of the function. So normal y equals sine of x has period 2 pi, and we kind of think about, okay, on the unit circle, that makes sense because as you go around the circle, this is a 2 pi angle. So it makes sense because as you go around the circle, if you go around another time, then you have another 2 pi. If you go around another time, that would be another 2 pi. And so every 2 pi, this function is repeating. Again, this is just assuming that we're always in radians, and from here on out, you are going to be in radians. So just stay in radians. Just like sine, cosine of x also has period 2 pi. And so, yeah, it repeats every 2 pi also because as you go around the circle, every 2 pi, the cosine's values are going to repeat. The word amplitude is specific. It is about what the distance is from the center of the curve to the top of the curve. And so this distance is what we call A for amplitude. Technically, it is from the center of the graph to the top of the graph, but it's the same distance as the center of the graph to the bottom of the graph. And for both cosine and sine, the amplitude is 1, generally. So like the one that says y equals sine x and the y equals cosine x, they both have amplitude that is 1. What we figured out on Desmos is that the functions y equals a sine bx and y equals a cosine bx, both of those functions have amplitude a and period 2 pi divided by b. And so the b is what's in here, and the a is right here. And so the period is something that we actually have to do something to do a calculation on, but the amplitude, just we can look at the graph and figure that out. Not the graph, the function. Okay, so the best real world example of what I have for you in terms of like what happens that works with waves and these kinds of sines and cosine graphs is sound, but sound, light, and a lot of other things that just sort of have like a vibration pattern going on can be modeled by using sines and cosine graphs. Yeah. So what you need to know is that pitch, which is about how high or low a note is or a pitch, it's like, so like this note is of different pitch from this note. And so you can kind of hear how the differences in the pitch of the sound is different. Okay, so what you need to know is that frequency is what the fancy word, maybe in physics, is for pitch. And so frequency tells you how often the wave is repeating. And so if we think about, okay, if this is sort of this is my range, and this wave is going up and down and up and down and up and down, the period is how wide this is, but the frequency is about how many do I have. So the frequency is how many periods are in a certain, I guess we would say time, because typically we measure frequency in terms of seconds, or how many times the wave goes up and down in seconds. Okay, so that's a lot of talking around something that doesn't really, there's something specific we're going to do. So that's just sort of a lot of like the describing what's happening. But here's what's happening. My example for you is 440 hertz. This pitch is a frequency. And so this is the pitch. If you play music, if you think about the A that's above middle C on a piano, if you don't, it's okay. It's just 440 hertz. It's a pitch that's sort of right in the middle of a piano keyboard. Okay, so the frequency of the A above middle C is 440. We often say A 440 to explain that frequency. What that says is there are 440 periods per second. And so that the frequency is about how many times that sine function or cosine function goes up and down and back to the spot where it started in the time that it gives you. So this is in seconds. So just for your reference, the octave below that is 220 hertz. And so this is the same note, but just one set lower. And so that is kind of interesting. That's half the hertz. I know we've talked a lot about pitch, but amplitude is about the volume. So the taller the wave, so if you have a wave like this, that is louder than a wave that looks like this. And that kind of makes sense too. It's like the pitch is vibrating more violently. It's going up and down fast, like higher and lower. Okay, so 440 hertz means 440 periods per second. And so if we draw a little diagram of what this wave could look like, if like this is my 1 second, so this would be 0 seconds, then this wave is going up and down and up and down and up and down 440 times. And so, not x times, I'm just gonna write times. Okay, so 440 times. So what is happening is this second is getting split up into 440 little tiny pieces. And so what we need to know is that we're splitting this 1 second into 440 pieces. This is what our period is. And if our period is 2 pi over b, because this is our formula for period, then we can solve for b in this equation. So let's see. Let's multiply both sides by b, and we get b over 440 is 2 pi. Okay. Then to get b by itself, let's multiply by 440. And we get b equals 880 pi. Okay, so what we know now is that our function for this a that rings at 440 hertz is, let's use sine, y equals sine, and then we're going to write 880 pi and then x. Because this is a sine function, with period 2 pi over, I guess it's 1/440th. That's the whole point. The period is 1/440th because we're splitting that 1 second into 440 parts. For comparison, let's look at that note that is 1 octave below, which is 220 hertz. So we're splitting now our second into 220 pieces. And so my 220 pieces is going to be, so my period is 2 pi over b, but that's going to be equal to 1 over 220. So now when we solve for b, let's multiply by 220 first, and we get 440 pi over b equals 1, and then we're going to multiply both sides by b. And so we get 440 pi equals b. So this is my new function, and for a note that rings at 220 hertz, our function would be y equals sine of 440 pi x. So my period is 1 over 220 seconds. If you want to kind of make a generalization about the pattern that we just saw, if we know what the hertz value is, then you can put in a function, you can put in an answer for h in this equation, and we'll use this formula. So the equation for a sound wave ringing at h hertz is y equals a sine of 2h pi x. So a is the amplitude. So this is something that we haven't talked about, but that's really related to volume. And h is the pitch in hertz. So volume, I mean like how loud the sound is. Okay, so we haven't done a lot of graphing yet, and so I just wanted to do these kind of quickly. But what you need to know is that we're looking for, okay, what is amplitude and what is period? So we remember that amplitude is A, and in this one I see that there's no A, so A is 1 here because there's like an invisible 1 written out here. Okay, the period is 2 pi over B. And so if I know that B equals 2, then 2 pi over 2 is equal to pi. And so this first function, y equals sine of 2x, is going to repeat not every 2 pi units, but every pi units. And so this red graph is going to kind of get split up into more pieces. The pattern is all going to be the same. The amplitude is still the same. So it's going to go up this far, but then it's going to go right back down twice as fast as the last one. And so I'm graphing sort of my landmark points to help me stay organized about how I'm graphing, and I'm going to do my best to make this look pretty. No promises. Here goes. And let's go down here this way too, I guess. Okay, looks like something like this. Okay, and so this is not perfect. Maybe probably this one is really the best one. But what you need to know is that this red graph, this one right here, is repeating twice as fast as the original one. Okay, this one I'm going to do in blue. I see that A equals 1, A equals 2, excuse me. And so my amplitude is going to be 2, but my period is written as B equals 1. And so my period is still going to be 2 pi over 1, which is 2 pi. So I'm still going to have these landmark points. These are all going to stay the same. What's going to change is how tall my graph gets. So instead of 1, it's going to go up to 2. And here it's going to go down to -2. Nope. Yeah, no, that's right. Okay. All right, so here's my sketch. Notice that I am not great at doing this. That is what our computers are for and our calculators are for. But we need to kind of get the idea. So what we did here is we saw two graphs. One of them we changed the amplitude and one of them we changed the period. This one though, we're doing both, and this one is the cosine graph. And so if I think about what does the cosine graph look like? Well, cosine starts at 1 and then goes down and back up from there. So let's figure out what is our amplitude. Is 3, because it's the 3 right here. And then the period is 2 pi divided by, and we see that our b is pi, so we're going to write pi. And so our period is actually the number 2, not 2 pi. Okay, so what does that mean? It means that our amplitude is at 3, and it's going to repeat every 2 units. And so it's going to go back up to here, and it's going to go back up to here, and it's going to go back up to here. Okay, and then what that means is that these values down here are going to be all the way down here. Let's see if I can do this right. There we go. Like that. Okay, so then this is going to be kind of a wild swing, back and forth and back and forth. Just kind of putting my marker points here so I can kind of try to keep myself organized. And here we go. Notice, is this perfect? Not even close. Is that okay? Yep, totally fine. Not a big deal. So you need to be able to find the amplitude and the period by using the formula 2 pi over b to get the amplitude of the function, or to get the period of the function, and then you just need to be able to sketch or use the graphing calculator to get a sketch of the graph.